Okay, here is a classic problem. I'm going to solve this two ways. The problem is a disk rolling down a plane. They do this a lot of times in physics labs where they'll take different objects and roll them down and show that they don't have the same acceleration. But I'm going to show you how to find the final velocity at the bottom of this plane for a disk. It's easy to go from there to other objects, but I'm going to do a disk. And I'm going to do this two ways. The first way, I'm going to use work energy principle to find the final velocity, and then I'm going to use forces and torque, which I like actually doing the forces and torque way better, but the work energy way is more common. So let's get started. Now there are a couple of background things that we need to know. I'll be sure to link some videos to those down below. But the first is this idea of moment of inertia of a disk. I wrote that down just so I wouldn't forget. And what does that have to do with anything? I'll show you. And the other is the work energy principle. So let's start with the work energy principle, which says the work is the change in energy. Now, after I do that, I need to declare my system. So let's say the system is the disk plus the Earth. You have to do this, right? You have to say what your system is, because I need to know what work I have on the system and what the changes in energy are. If I have the disk and the Earth as my system, I can have gravitational potential energy. If I only had the disk, then there's no gravitational potential energy, but there'd be work done by gravity. So those kind of choices that you need to make. And so in this case, I'm going to pick the disk plus the Earth. Now, I still need to consider the work done on my system. So I'm going to draw a free body diagram for the disk as it's rolling. And it's released from rest. So here's my disk. And so you think about what forces are acting on this. Well, we have long-range forces and we have contact forces. So the long-range forces are things that act on it without touching, and obviously that would be the gravitational force. So I can draw that as a vector acting on the center of mass of the object, pointing straight down towards the Earth. Now what's touching it? Well, the plane's touching it, right? So there is a contact interaction between the disk and the incline. And so there's going to be two forces due to that contact. There's a normal force. I'll put it right here like that. And that may look weird, but I'll draw it like that for right now. And this is a force that's perpendicular to the surface of the disk, of the incline. And it's at the point of contact. And the other force is a frictional force. And it's going to be going this way. F, friction. And imagine if there is no frictional force, you wouldn't have a rolling disk. You would have a sliding disk. So here's, it's almost the same size. So here's a penny to represent my disk. And I can draw a little line there so you can see that it's not rotating. So if there's no friction, it would just slide down there. And it would be the same as a block sliding down a plane. But instead, this disk is going to roll like that. Okay. And so that frictional force causes it to change its angular stuff. But which of these forces do work? Okay, that's the most important thing. This first one, the gravitational force, does not do work on the system as it moves from here down to here. Why? Because the disk and the Earth are part of the system, so this is an internal force. This is why I have change in gravitational potential energy. So that doesn't do any work. What about the normal force? Well, we can define for a constant force, I can say the work is F dot delta R. So delta R is going to be this displacement this way, and the force is the normal force. But these are perpendicular. And so this could be written as F delta R cosine of pi over 2. I'll write it as like that. That's the angle between the displacement and the force. And the cosine of pi over 2 is 0. So the work done by the normal force is 0 because it's perpendicular to the displacement. 0. Okay, what about this frictional force? Does the frictional force do work? Well, it's pointing in the opposite direction as the disk, but work is the force times the displacement of the force. This is how far the force moves, not how far the disk moves. And so in this case, since the disk is rolling, once it turns, the point of contact is at a new point, but the force itself, the friction force, doesn't actually move. So the displacement for friction is 0, and it does no work. And you can imagine that a different case where it was sliding with friction, then there would be displacement for the friction. But in this case, there's no displacement. It's just at a different contact point. It doesn't do any work. So the total work is 0. Now, what kind of changes in energy do I have? Since I have the disk plus the Earth, I actually have 3 kinetic energies. I have a translational kinetic energy due to the rotation of the center mass. Let's write this down. K translation is 1/2 mv squared. That's the translational kinetic energy. I have rotational kinetic energy, Kr. It's 1/2 I omega squared, and that's where the I comes in. So this is the moment of inertia of the disk, which tells you how the mass is distributed about the disk. Omega is the angular velocity of the disk, how fast it's rotating. And so that's the rotational kinetic energy. And then finally, I have gravitational potential energy, UG, I'll call it, as mgy. Now, all of these don't matter. What matters is the changes in energy. And that means that I can pick whatever value of y I want to calculate this. And I'm going to go ahead and calculate, say, y equals 0 down there. So now if I put this together, there's no work done, 0, change in kinetic energy, rotational, plus change in translational, plus change in gravitational potential. So that I can write that as k rotational 2 minus k rotational 1 plus k translational 2 minus k translational 1 plus u potential 2 minus u1. Now half of these terms are 0. If I release this from rest, then the initial rotational and translational kinetic energies are 0. So that's 0 and that's 0. Also, at the bottom down here, it's going to have no potential energy. So U2 is 0. Okay, so now I can start writing things out. I'm going to switch to a new piece of paper because that's what I do. So let's say 0 equals the final rotational 1/2 I omega 2 squared, and then minus 0, and then I have the translational final kinetic energy plus 1/2 m v2 squared, and then minus the initial, which is m g h. So that is my new energy equation, and I want to solve for v2. But I have a problem here in that I have an angular velocity and a linear velocity. But if it is rolling without slipping, and this is important, rolling without slipping, then v equals omega divided by r. That has to be true if it's rolling without slipping. No. Why don't I just have these little mind things that just kind of v equals omega times r. But, I just blank out because I'm thinking about the next step. But what happens is I catch that because I say, okay, look, this is radians per second times meters gives you meters per second. And that's one way to check it. Okay, so I do know that. Let's go ahead and solve this for omega. Omega equals v over r. Now I can plug that in here. I can also plug in I equals 1/2 mr squared for a disk. So I get 0 equals 1/2 times 1/2 mr squared. Omega squared is going to be v squared over r squared. V squared over r squared. Plus 1/2 mv2 squared. That's a v2. Minus mgh. Now these two terms, this is 1/4 mv squared, those cancel, plus 1/2 mv squared. So I get 0 equals 1/4 plus 1/2 is 3/4. Yeah. 3/4 mv2 squared minus mgh. Now I can add mgh to both sides, and I get 3/4 mv2 squared equals mgh. The mass cancels. Multiply both sides by 4/3, and take the square root, and I get V2 equals the square root of 4/3 GH. Yeah, that's right. That's the final velocity at the bottom of the thing. Now, just as a quick comparison, what if I had the same situation, but now I have a frictionless block of ice? In that case, I could do the exact same problem. It just wouldn't have any rotational kinetic energy. So I could get down to the same thing up here without that term. So there would be work is a change in energy, is a change in translational kinetic plus change in gravitational potential, and that's equal to 0. So I'd have 1/2 mv2 squared minus initial minus mgh equals 0. And if I solve that for V2, I get V2 equals the square root of 2GH. This is sliding, rolling. So which one's going faster? Well, I have 4/3 versus 2. Which one's greater? 2. So this one's going faster. Okay. So, and that makes sense, right? Because some of the energy has to go into rotation, it's not going to end up going as fast at the bottom. And this is using the work energy principle. Okay, are you ready for part 2, which is I find more interesting? Let's start again. I'll draw my picture. Theta, H, and let's just draw this at some point. Oh, that's a bad circle. Okay, and there's my radius R. It's giant this time. But I want to draw all the forces acting on it again. So here's my disk. Now I have the gravitational force, mg. I'm going to put the normal force, even though it was, I guess I should do it right here. I could start it from right there, but it just looks a little cleaner right here. Okay, so there's my 3 forces acting on the object. It's a rigid object. So for a rigid object, I actually have 2 things. I can say F net vector equals mass times acceleration vector. And I can say, now this is this is the simpler version of torque. Okay, so I'm going technically you could write it as a vector, but I'm going to say the torque about some point is equal to I times alpha. And this is true for a the forces have to be equal, relate to the acceleration, and the torque has to be related to the angular acceleration. This is how fast the object changes its rotational velocity. Okay, and it is, right? Because as it goes down, if it's going to roll without slipping, it has to rotate faster and faster and faster. Okay, let's start off with this right here, and then we'll get down to that, because there's some pieces that we need to understand for this whole thing. So if I want to do this problem, the first thing I should do is pick my x and y axis. And I'm going to be smart here. I'm going to pick this as my x-axis, and this as my y-axis. And if I do that, but the x and y-axis are not real, so I can pick whatever I want. But if I do this, then I have an acceleration in the x direction and no acceleration in the y direction. If I pick this as my x-axis, then it's both accelerating in the x and the y direction, and that makes it a little bit more complicated. Okay, so if I do that, then I can say, actually, this equation becomes, I get 2. I get F net x equals mass times acceleration in the x direction, and F net y equals 0. Because it doesn't accelerate in the y direction, it stays on the surface of the incline. So what forces are acting in the x direction? Well, let's draw my diagram right there. There's my x. There's my y. And if this angle is theta, and there's my gravitational force, this angle is also theta. So this angle's theta. So I have two forces in the x direction. I have this component of the gravitational force, there's my right triangle, and I have the frictional force. So I can write this as equal to, and this is my positive x direction, if this is mg, this is going to be mg sine theta. So it's going to be mg sine theta. That's the component of the gravitational force in the x direction. But I also have this friction force in the negative x direction, so let's just add that. F friction equals max. So what's the acceleration? Well, I don't actually know because I don't know the frictional force. Now, you may be tempted to say, oh, the frictional force is equal to the coefficient of static friction times the normal force. That is not true. Technically, it's this. Less than or equal to the coefficient of friction times the normal force. So if you did this to calculate the frictional force, you may give it too much torque and it actually rotate too fast. In fact, friction does whatever it needs to do to prevent it from slipping. That's it. Okay. So we can't use this or this to find the frictional force. So we're just stuck with this right here. Okay, now let's go to this situation. This says the torque is equal to the moment of inertia times the angular acceleration. And this is a shortcut version. Really, torque is way more complicated than that. But let's just pick a point about which to calculate the torque, and it makes sense to calculate about the center of mass. And torque is defined as R times F times sine of alpha. Let's put it as, no, I can't use alpha. Let's use beta. Where beta is the angle, I gotta spell it right, angle between R and F. And R is a vector from the point of rotation to the contact point. Okay, we call that the torque arm. Okay, so let's look. We have three forces. So we have three torques we have to consider. First of all, this gravitational force. What is the torque due to the gravitational force? Well, it passes right through the point of contact. So for this one, R is equal to 0. And if R is equal to 0, the torque is equal to 0. So I can write this as torque O equals RG times mg times sine of beta g plus R friction times F friction times sine beta friction plus R in sine beta n. How's that? And there is a direction, there's positive and negative directions, but I don't think we need to worry about that because right here, Rg for the gravitational force is 0. Now technically, gravity acts on all parts of the disk. However, we can use a single point and get the exact same answer. Okay, and that's the center of mass. Technically the center of gravity. Okay. For the frictional force, we need to do that. That's fine. The normal force also, you'll see here, if I call this my Rn, then the angle between this and that is equal to pi. And the sine of pi is 0. So this also has 0 torque. So the only thing I have left is this. And what's the angle between the friction force and the point, the Rf? It's pi over 2. Sine of pi over 2 is 1. So the torque is equal to the radius of the circle times the frictional force. And that's the only torque on there. Now this has to be equal to I times alpha. And I know what I is, so that's going to be 1/2 mr squared times alpha. Now, if I can get an expression for F in terms of the acceleration, I'm going to be golden, right? So here I can say that alpha equals A over R. And you can get that straight from omega equals V over R. And if I divide both sides by delta t, and I get if I say delta omega over delta t equals the angular acceleration alpha, and that's going to be 1 over R delta v over delta t. And that's the acceleration. That's the linear acceleration. So that's how you get this right here. So if I put that in, I get 1 half m r squared alpha, which is ax over r. And so now if I solve this for F friction, I get the r, I can divide both sides by r, and I get r squared over r, so I get 1 half m ax. That's the force due to the frictional force that has to be there. Has to be there in order to make sure that the disc rotates, rolls without slipping, right? That's what that has to be in order to make that angular acceleration match the linear acceleration so that it doesn't slip. But now I can take that and put that in up here, and that's what I'm going to do. So let me write these two equations. So I have this one, mg sine theta minus the frictional force equals max, and then I have the frictional force equals 1 half max. So let's substitute this in up here, and I get mg sine theta minus 1 half max equals max. So I'm going to add this to both sides, and I get mg sine theta equals, now I have max, so I have a half plus 1, so that's going to be 3 halves. 3 halves max. The mass cancels. And I want to solve for ax, so I get ax equals 2/3 g sine theta. And this is actually really nice because now I have an expression for the acceleration and I can see that it's constant. We didn't get that from the previous work energy case. We only got the final velocity. Okay, but now I need to find the final velocity. So here I need to do a couple of tricks. I can do, you could use the kinematic equations, but let me do this in the way that I like to do it because this is my video. It's not your video. So, and normally at 20 minutes I'd take a break and tell you a story, but I'm not going to do that. We're almost done. Okay, so I'm going to say the acceleration in the x direction, I'm going to drop off the x, is delta v over delta t. That's going to be v2 minus v1 over delta t. If I solve that for v2, I can multiply both sides by delta t, and I get v2 minus v1 equals a delta t. And then I can add v1. I get v2 equals v1 plus a delta t. But I don't know the time. Okay, so what do? Well, there's another definition of the I can use for the average velocity. I can say v average is equal to v1 plus v2 over 2. If the acceleration is constant, I can just take the velocity at the beginning plus the velocity at the end and divide by 2, and that would be equal to the displacement, which in this case is s, over delta t. Average velocity is change in position over change in time. Remember, s is that length of the triangle right here, s, theta, h. So I can take this and solve for delta t. So if I multiply both sides by delta t, I get delta t equals 2s over v1 plus v2. Now I can put this in up here. And I know you're thinking, hey, this is crazy. Just use the kinematic equations. No, I'm not going to use the kinematic equations. That's a sign of weakness. Okay. So now I have this equation is v2 equals v1 plus a delta t, which is 2s over v1 plus v2. Now I know a. Okay, I'm going to put that in just a second. So now I'm going to say v1 equals 0. So that means v2 equals 2as over v2. I multiply both sides by v2, and I get v2 squared equals 2as. So v2 equals the square root of 2. Now I'm going to put in a, so times 2/3 g sine theta times s. Now I'll look up here. If I say sine of theta, it's going to be opposite h over the adjacent s. So h equals s sine theta. That's h. So now I get the square root of, that's all the way down, 2 times 2, which is 4/3 GH. And that's exactly what I got before. Identical. That's from My Cousin Vinny, right? Identical. But that's not how you spell it. Okay, so there you go. Yeah. You know, what if, and I did say, what if you want to do this for a sphere? Well, all you have to do is go back and say, let's say a sphere, the moment of inertia is 2/5 mr squared. And this, everything's going to work out the same. You're just going to have to go back up to, where is it? Let's see, where my previous... Right here, in the work energy, you just change that 1/2 to 2/5. And everything else is the same. You get a different answer. But there you go. Okay. Hope you enjoyed that. I had fun.